Welcome to Jumping Airgaps. I'm Monta Elkins from a little company called FoxGuard. We do industrial control system security. We'll talk a little bit about kind of the history and the future of security, and in particular, kind of jumping air gaps. I started exploring this concept this year. So what's an air gap? What's an air gap? Right. Right, so we're going to try to protect systems by disconnecting them from the public internet or from any kind of internet. Normally everything is sort of wired up, but we're going to separate this thing out because we think that's probably the ultimate in network security is to not be connected at all. So what better for hackers to look at but, the ultimate in security. And in particular, we work in the kind of electric space and sort of in the nuclear space, another place where these disconnected networks are kind of the pinnacle of security there. So we started playing with these. And here's the other thing is that I want you to know that none of this is magic, right? If I can do it, you guys can do it. This is the first thing we played with. This is a little teensy microcontroller with a cadmium sulfide light detector on there. And what we did was we modulated the caps lock light to pull data off the device. It's a stupid hacker trick, but I can pull data out of there that will probably get past your, data exfiltration protection. If you guys, we're not really circulated together. You can come up and see these later, or maybe we can pass them around. You can pass them around if you want. Try to make sure they get back up here. It's just random hardware. Lots of fun, but it's really not that hard. And matter of fact, though, you hear about these things, and they've been done forever, right? This is a watch from 1995. Anybody recognize this? Well, you had one?
I had one because it was broken, but it was put on the screen and then sent information over it.
Right, yeah, I've got one now. I didn't at the time, but now it's cool. So the way you could program this before you had PDAs was that you would hold it up to the screen and it would flash data, and this was a light sensor, right? So you could put your appointments in here. It doesn't work with the new LCDs. You have to have a CRT. But in any case, so, we've been using light to transmit data forever. Back way before that, probably in the 60s, who knows what this is? A modem, a dial-up modem back in the day before we had cable internet. And they had blinky lights on them. And in particular, they had an RX light and a TX light that would blink as it received a bit or as it transmitted a bit. And some smart folks at some three-letter agency figured out that you could point a telescope at that, and you could read those blinks, and you could pull the data off of that from anywhere you could see those blinky lights. Well, pretty cool. And then eventually would kind of smear out the lights. But whatever. We've been doing this for a long time. We also did ultrasonic transmission of data, right? This is a pretty non-traditional way to jump an air gap, but this is a little Arduino with a little piezo speaker, and then my partner wrote a cell phone app that would capture the data and decode it. So we could transmit hello messages and send a little bit of data, and you could pick it up on your cell phone and look at it. Kind of cool, but in today's day and age, it's really not that hard. This stuff used to be, right, very complex, complicated stuff. Today, not so much. Matter of fact, we've been using ultrasonic forever. Does anybody know what this is? This is, and I brought one. This is the shiny version. I took the picture of that one because it looks older. This is a Zenith Space Command. It's a remote control, ultrasonic remote control. The new ones are what? Infrared, right? But they run at a 400 kilohertz modulation tone, which comes from these ultrasonic. The history is in the ultrasonic. Another quick question, what kind of batteries does this take? Any idea? No batteries at all. How many transistors? 0. How many capacitors, resistors? 0. This is an entirely mechanical system. They are little tuned metal bars in here, and when you push this button, the clicker, anybody heard them called clickers? Right? Now you know where some of the terminology comes from. Hammers the end of this bar at an ultrasonic frequency you can't hear, but that the television can pick up. So we've been using ultrasonics forever as well. Radio frequency is the new hotness. But radio frequency transmission is dead simple. Any place you can blink an LED, if you can have some dedicated hardware, like an SDR nearby, dedicated hardware means that you can pick that up. Just a little bit of line in the LED. So again, I set up an Arduino, I send out my call sign and a little hello message. Actually, I'm running to capture the flag. Oh, I probably shouldn't say this. Don't tell anybody. There's going to be a capture the flag where they can pick up passwords off of decoding information coming out of an Arduino over your SDR. But that's kind of dead simple, at least on the transmit side. And now, because of the way technology has changed, it's pretty simple to receive and decode with some dedicated hardware your $15 SDRs. But any place you can blink a light, wiggle a pin, you can transmit RF, pretty much. I'm doing this one at 57,600 kilohertz. Pretty low. One of the reasons 57,600 is nice and low. The Arduinos don't have a lot of speed, so I can do that. Anybody recognize the number 57,600? It's one of it's one of the multiples of the modem, 12, 24, and 56. So my thought being is that even if I don't have high-speed dedicated hardware, maybe I can do it with things that have serial ports straight off the serial port and generate RF frequencies at 57,600, and sure enough, I can pick them up over short distances. But we've been doing that forever too. These, anybody, just raise your hand. Anybody know what these things are? Either of these? All right, you're as old as I am. What does? but right, this is where it's happening. Yeah, so right. So these are. If you did industrial control systems in the 60s and the 70s, they ran off of these things. You realize you program these with the switches on the front, right? I actually did bootloader tape loaders by programming them off the front. But in any case, in the 60s or so, we realized with some dedicated hardware, the dedicated hardware being an AM radio, that we could write programs that generated audio tones and play simple music. So we're using computers to run different instructions. They're toggling power off and on internally, and we can pick that up externally and primarily use it for entertainment. Oh, look, the computer can play a single voice of music, right? Not very high fidelity, but you can do it. Then we get up to implants. So this is my new USB cable. Oh, I bought a couple of different ones. This is the Apple version. I'll pass it around. The cool thing about this USB cable is your SIM card goes in here in the slot, right? And it will transmit voice and GPS location back. And you always have power because the person, right, you keep this plugged up to the power and then you plug it up to your phone. So this is your hardware sort of data. Ooh, aliens are coming. Your hardware sort of data exfiltration. I paid like $15 for that. You know why? Because the $5.99 ones were sold out. So this stuff is incredibly cheap, comes straight from China. It doesn't say that it does data. It's just doing voice and location. So it says maybe the data goes straight back to somebody else. I don't know. But yeah, you slide your SIM card there, and that's the way it works. But we've been doing these things forever too. I see you laughing. You know what this is? Yeah, the thing. Anybody else know what the thing is? Yeah, okay, right. So we won't do it justice. It's a story in itself. But the short version is in about 1947, I think. A bunch of Russian school children presented this hand-carved seal of the U.S. to the Russian ambassador, who promptly hung it on his wall, right, where it stayed for, I don't know, 4, 5, 6, 7 years and 3 different ambassadors. It turns out on the inside, it was basically a passive device. It's all hollow, but sound would change its resonance cavity, and if you illuminated it with microwaves, it would modulate an audio signal that you could pick up, right? Radio frequency with an audio modulation that you can pick up. So that was pretty incredible technology, by the way. There's no active parts in there. It's powered remotely by microwave. You know, maybe that's where some of the tinfoil hat myths come from. Is that? By the way, anybody heard of one of those musical devices called a theremin? He helped invent this thing, just by the way. Yeah, I thought that was fascinating. He also did the early, you know, you've heard of the laser microphones. I'm doing some work with that right now. You bounce a laser. He did that too. Before there were little lasers, he did it with infrared, nice and invisible. Yeah, I just thought he made silly music. Who knew? So it turns out, even though the air gaps are great, they are often impractical. Even in industrial control system, it turns out that we need data out on a regular basis. We need some information about the system for tuning and efficiency and maintenance purposes to come out on a regular basis. So we set up those networks. By the way, what do you think? What's the sort of furthest air-gapped industrial control system you can think of would be? Satellites, International Space Station, right? They're pretty far out there. They've been owned by viruses at least twice. So just saying that there are some other ways to jump these air gaps, but I'm more interested in a continuous communication channel because sophisticated attacks in the ICS space, it's not, hey, can we make something happen? Can we turn this thing off? Let's say it's a power plant. Can we turn off a power plant? Great. That's old hat, right? The state of the art in the research in this space is not can I turn off this power plant? Can I find the most expensive piece in this plant, the most difficult to replace, and can I destroy it in such a way that it will take you a long time and a lot of money to destroy it? And what that means is that you have to do research for a while. You need an existing network connection for a while to understand what happens in that infrastructure so that you can do the most damage. So that's sort of the state of art in the ICS space. That's where real security happens, let me tell you. You're going to be facing the most sophisticated, well-funded nation-state attacks first in industrial control systems. So typically we think about, we're going to move into, who's heard of a data diode before? Unidirectional gain? Oh man, well, so that's much more than I expected from a. I generally speak to ICS very specific audiences, right? But no, that's about 50% in case you couldn't see. In general, when we're talking about one-way communication, we often think of it like this, where if you had some intelligence agency, some three-letter agency, they want to be able to collect secrets, but they want to make sure nothing comes back out, right? They want to be able, it would be awesome if you could just make sure that data went in but didn't come out. In industrial control systems, it's the other way around. We would like data to be able to come out so that we can figure out, is it working right? Can we bill people for the product we're making? We're making water or chemicals or pharmaceuticals or whatever. But we don't want data to go in. We don't want people to be able to send in any type of control message for this system, right? You can't change it. It's okay if you can read what's going on, but you can't change it. So it would be great if we had something like a data diode. The data diode comes from this concept of a electrical diode. If you are an electronics hobbyist or practitioner, you know that a diode only allows electric current to flow in one direction, not the other. And there are a couple of patents for data diodes we won't really go over, but the principle works something like this. Imagine this connection where on this side of this, if we consider either this or maybe this whole thing a data diode, or perhaps a unidirectional gateway. I don't necessarily have time to discuss the difference, but that you can only send data in this direction, and that's guaranteed by the physics of its operation. So you basically have a flashlight on this side and a solar cell over here. And this system can blink this flashlight so that this system can read this solar cell and we can send information in this direction. But there's no way that you can blink the solar cell and read it with this flashlight. So the physics prevents data from coming back in this direction. So that's the basis of your data diode, and if you will give me a little bit of leeway of your unidirectional gateways. Now, they call a data diode unhackable. So, and, you know, a pretty fair term as far as it goes. If we think about other devices, other computer equipment in the security space, imagine this firewall where if I'm able to put any malware, if I can get malware on the space station, I can get malware on here. What I want is a continuous connection. If I can put malware on this firewall, if I can change its configuration, can I allow data to go in both directions across this firewall? Yes? No? Yeah, if I can change the configuration of this firewall, if I can put malware on it, I can make it send data in both directions. If I can put malware on both of these computers, can I make the solar cell generate light and this flashlight receive it? No, so that's what they mean by unhackable, right? This is enforced by physics, which is also a challenge. So here are some of the actual pieces used. Again, if you want to talk, we can go into a little more depth. But I start by building a model based upon the patent data because, you know, my company, these things start at 50,000 and easily jump to 150,000, and they won't buy me one just to break. So, but I model it using the same setup from the patent, and the implementation is like this. Although actually I have this data diode going in this direction. So this represents generating the light in the little device, which is an opto-isolator. And this is the part that receives the light. There's no way to generate the light and receive it on this side, right? So this is sort of the computer that supports this half. This is the computer that supports this half. And it only lets data go in this single direction. In my model, I built out the model, you know, to scale, but I didn't really have time to paint it. Now, and this might represent the cooling tower of your important plant or some such. And this might represent the output, right? Just a simple representation of how this works. And this light says, hey, it's doing the right thing or not. And this is just the video, the basic demo. This cooling tower is running, and as we measure something that happens inside the plant, it's able to send data through this opto-isolator, this light and detector, that's read outside the plant. That's the way that's supposed to work. And we can go outside the plant and we can do things like, we can reset it, but there's no way to send information back in this direction. That doesn't work that way. The same example. So, but the concept hasn't changed, but the universe has actually changed in the past few years in that these processors tend to have more power than they used to, and we become a little bit smarter about things like software-defined radio. So it turns out that transmitting a radio signal, if I'm going to send data this way, is easy. We know that. I can blink a LED and transmit data. People have been doing that forever. But we needed specialized hardware to read it, an SDR dongle or an AM radio. But the power of these new processors are such, I can use the built-in analog to digital converter, write software-defined radio software, and read this transmission over a short distance just with the power built into the chip. No additional hardware, nothing but software. This isn't an implant that I have to put in. This is an attack I could send by software. If I can get malware to the space station, right, you have to give me that I can put malware on both sides of this. What I want to do is maintain the connection. So in this side of the demo, me flipping these switches is when I'm installing the malware on both sides. You don't have to give me we transmitted malware to both sides of this device. But at this point, what I'm able to do is transmit a signal by RF that I can pick up over here so that if you watch the fan over there, when we push the button, the fan stops, the light comes on. Thank you very much. So a representation of a new style of attack in the industry because the universe has changed, right? And we see that a lot, that air security might be the same this year as it was last year, but the universe changed around it and made it less secure. In particular, and we can cut the wires and go through that example to see that it works. It's not a break of any particular product. This is a representation built off of the patent information. But in particular, so they do consider RF when you design these things like Tempest, right? You look at this device and you see if it radiates anything outside. There are two issues with that. Issue number one is that measurement is not made assuming that this thing is operating incorrectly. You measure that with the original firmware. Issue number two is that they build these inside RF shielded boxes so that you can't get radio signals outside of there anyway. For me, that's a benefit. That means it's nice and quiet in there and it's not hard to pick up that signal out of the noise. All right, so we are at the end. I just want to say that this is if there's anything new about this attack, and I think there is a bit, it's using existing hardware to form an SDR function in a way that probably wasn't anticipated by the original designers. I also hope that this inspires people to do these attacks on additional hardware and on real hardware. It won't work on some of these. Some versions of data diodes use a fiber optic line and are separated by a large distance. Some of them are built into the same box. That's where I'm looking at. So some places it won't work, but some places it will. And again, back from the sort of philosophical view, a lot of the security that we do, which was once secure, becomes insecure, not as much because what we were doing had changed, but because things changed around it. Things like industrial control systems, they were secure when they were built, and they're the same as they were, but now they're not secure because things changed around them, like the internet was born. Right? So things changed around them that made them less secure. So I also want you to consider that your security practice is a journey, not a destination. It's always something that has to be reconsidered in light of new technologies, both technologies in terms of hardware and availability. You know, software-defined radio is the hotness now. That's why it's easily accessible for me and for you and for others where it wasn't before. So with that, I'm Monta Elkins. Feel free to stop me and talk me along the way. If we have any of the pieces, let's pass them back up. And I hope you have a great conference. Oh, questions? Do we have question time or? All right. You know, somebody else runs my time. I'm just here to look pretty.
Very, very quick. Are you giving something like this talk anywhere else this weekend?
I am not. No, you are the only audience. If you happen to be in California in a few weeks at an ICS specific conference, I will be doing a longer version of it there. Sorry, you guys are exclusive.
What conference is that?
It's Energy Sec in Anaheim. Do you know it? You going? Are you going to be there?
Yes.
Oh, well, you should be at this. We'll do the long version. All right. Thank you very much.